Okay, so let me start. So first of all, I would like to thank the organizers for giving opportunity for me to give this presentation in this nice workshop. So I'm Kenichi Saikawa from Kanazawa University, and I'd like to talk about the actions from global strings. And this talk is based on the recent work in collaborating with Javier Redondo and Alejandro Vaquero. And the result is not published yet, but I hope the preprint will be available soon in archive. Okay, let me start. So the motivation of this work is about the prediction of the action dark matter mass from theoretical point of view. So throughout this work, I'd like to focus on the so-called QCD axion. So there is a one-to-one correspondence between the action mass and decay constant. And the current situation is that there are a lot of there are large mass ranges, a large field space, which is not so tightly constrained, and there are a lot of possibility to having actions or as a dark matter in various mass ranges. And there are a lot of experiments such as are proposed to explore the actions in various mass ranges. But it might be useful to have some theoretical estimate on the typical mass of the action dark matter, because this kind of information can be used for the guide for the future experiments. And such information might be used as to interpret the experimental results. And to have some estimate, we basically use the cosmology. Namely, we calculate the action dark matter abundance and assume that this is given by just a function of the action mass, which is a free parameter, and requiring that the action is 100% of the dark matter. We can invert this relation to have some estimate to the action mass. And but in order to give this kind of estimate, we have to introduce some assumptions in the cosmology. And here I would like to focus on the so-called post-inflationary scenario, where there are several different possibilities. And for instance, if the Peccei-Quinn symmetry is broken before inflation, which is a pre-inflation scenario, we can also have an estimate of the action dark matter abundance. But in the pre-inflationary scenario, there is some ambiguity related to the initial misalignment angle, which is already discussed in the various speakers in this workshop. But this kind of uncertainty related to the initial condition might not be so problematic in the post-inflationary scenario, because we expect that action field is randomly distributed after the Peccei-Quinn symmetry is spontaneously broken. But in that case, we expect formation of the cosmic strings in the early universe. And after that, and furthermore, we also expect the formation of so-called domain worlds at around the epoch of the QC phase transition. Domain was a seed-like object which is attached to strings. In this talk, I just assume that domain world number is equal to 1, or in other words, assume that the degeneracy in the low energy vacuum, there is no degeneracy in the low energy vacuum. And in this case, one domain world is attached to the strings. And immediately after the formation, the system becomes unstable and starts to collapse afterwards. And it is expected that the energy density stored in these strings and domain worlds are radiated as axions, which can become the dark matter at the present time. And if we understand precisely how axions are produced by this complicated process, in principle, it would be possible to give a sharp prediction for the dark matter mass. So in this case, the uncertainty in the prediction in the dark matter mass is exactly corresponds to the uncertainty in the calculation of the action number from strings produced by strings. But this kind of estimation turns out to be extremely difficult because of the fact that there exists two extremely different length scales in the system. So one is the Hubble radius, which corresponds to the typical distance between the two neighboring strings, which is a macroscopic scale. But there are also very small scale corresponding to the size of the core of the string. And this scale is given by the inverse of some typical mass scale, which is roughly given by the order of the Peccei-Quinn scale, which I denote MR. And if we estimate the string tension, which is the energy of the strings per unit length, it is known that this tension acquires some logarithmically divergent contribution from the field surrounding the strings. And this logarithmic contribution has a cutoff by these two different scales. Now, the realistic value is the ratio between the Peccei-Quinn scale to the Hubble parameter at the QCD phase transition. And this becomes a very huge number, 10 to the 30. And in terms of this log parameter, this implies that the factor is about 70. So we expect that there is actual string is 70 times heavier than naive estimate. And because of these corrections, it may affect the dynamics of the system, which may also affect the estimate of the dark matter abundance. However, it is impossible to reach such a large hierarchy in the simulations with limited dynamical ranges. And basically, you have to perform extrapolation by many orders of magnitude. That is extremely difficult. Then, in order to calculate the axion dark matter abundance, one important quantity is the spectrum of radiated axions. So here I introduced this quantity F, which is given by this formula. And this is basically the time derivative of the axion energy density spectrum times scale factor to 4. Then, so if there's no production or absorption of the axions, this combination is constant. So this time derivative vanishes. But if there is some production of axions, this has some positive contribution. Then we can compute this quantity for each momentum of radiated axions and plot it as a function of k. And the result looks like this. So there are two cutoff scales corresponding. The one is IR cutoff corresponding to the Hubble parameter, and the UV cutoff corresponding to the string core radius. And we may characterize the behavior at the intermediate momentum as a simple power law, K2 minus Q. And in this parameterization, the value of this exponent is extremely important for the calculation of the axion number, which is given by this right panel, where the y-axis is the axion number and the x-axis is the value of the exponent. And we see that the value increases if the Q takes a larger value. This simply means that for larger value of Q, the spectrum is sharply peaked at the lower momentum. So there are a lot of soft axions are produced, and accordingly, there are some enhancement in the axion number. On the other hand, if Q is small, typically smaller than 1, then some higher momentum axions are also produced. And accordingly, the action number itself can be suppressed. And the action dark matter abundance has been in this scenario has been calculated by several authors so far. But the current status is unfortunately there remains some controversy on the estimation of the action abundance. So here I just plot the action mass given by several different authors and plot it as a function of the year of the publication. And you see some difference in the results. And in particular, recently there are two important papers. One is published by Gorgetto, Hardy, and Biardolo, and they concluded somewhat higher mass. And on the other hand, the group of Malte Bushman and his collaborators performed some sophisticated simulations and concluded a somewhat smaller value for the mass prediction. And it seems that two results are inconsistent with each other. Basically the difference of these two results can be attributed to the different assumption of the spectrum. So this group assumes that the Q becomes much larger than 1 when extrapolated to the larger value of log, while this group concluded that Q is constant and equal to 1, and accordingly the smaller mass is predicted. So it appears to be important to understand what is the systematics exist behind in this kind of analysis. And it is important to improve the analysis method to give some more accurate estimation of the action radiation spectrum. So with this motivation, we have also been working on the large-scale simulations of action strings. Here we are taking a very conventional approach by solving the classical equation motion of the classical complex scalar field on the static lattice. But we are allowed to use some supercomputers at the Max Planck Computing and Data Facility, and also some computers in the Osaka University. And thanks to these huge computing resources, we have been increased the box size of the simulation up to the 11,000 cubed. And we also performed a lot of smaller size simulations. And we hope this kind of data can be helpful to understand the systematics on the calculation of the action dark matter abundance. And in the following slides, I would like to show some results of these simulations. So first thing to note is there exists the behavior so-called attractor. So here I plot the string density parameter Gzi, which basically counts how many strings exist in the simulation box. And I plot it as a function of the log. And this figure shows a result of the small scale simulations, 2,000 cubed, with different initial string densities. So we have done a lot of small scale simulations with different initial conditions, and confirms that the different initial condition tend to converge into the similar behavior at late times. And we can even possible to find a line at which the result is least sensitive to the change in the initial condition. And we assume this dashed line as a line of the attractor. And we use this initial condition for larger fiduciary choice for the initial condition for the larger simulations of with the larger box sizes. And by using this data, we also checked how much is the impact of how is the impact of the different choices of the initial condition on the estimation of the action spectrum. And here I show the plot of the spectral index as a function of log for different choices of the initial conditions. And here we can see there are some trends that the underdense initial condition lead to the more UV dominated spectrum. So under dense cases, there are not so many small scale fluctuations. So the lower momentum actions are more produced, so that the Q is a larger value of the Q is obtained. On the other hand, the overdense cases are the smaller value of the Q is obtained. So by looking at these differences, we see that it is important to have initial conditions closest to the attractor, because otherwise we may misinterpret the trend, overall trend of the behavior of the Q when we use them as in the extrapolation. This is one thing. And the another aspect of the systematics in the analysis is the existence of the oscillation in the action spectrum. So in this left panel, I plotted the evolution of the energy density of one mode, the time evolution of the energy density of the one mode. Namely, instead of plotting the spectrum as a function of k, we fix the value of the co-moving momentum k, and for each value of k, we plot the time evolution in the x-axis. And we see that there are two different regimes in the evolution, and the boundary of these two regimes is interpreted as a horizon crossing, because it always happens when the momentum of the mode becomes comparable to the Hubble scale. And after horizon crossing, we see that there are some oscillatory features in the mode evolution. And this is not the numerical artifact, but this is somewhat expected from physical grounds. Namely, if we forget about the strings and just solve the field equation of the free scalar field in the expanding background, then we found a solution that the mode amplitude is frozen outside the horizon, but starts to oscillate with the frequency k after the horizon entry. But actually, and we observe such kind of a frequency in our data. But the frequency is, strictly speaking, frequency is 2k, because in this case, the energy density is the field amplitude squared. But anyway, the existence of this kind of oscillation appear to be problematic for the calculation of the action spectrum, because if we take the time derivative of these oscillatory features, for instance, if we take compute the time derivative by finite difference method, it leads to a lot of contaminations on the final result of the spectrum. And this may contaminate the overall trend of the spectrum. So after noticing these contaminations, we have developed some analysis method that filters out this high frequency oscillating component and just pick up the low frequency trend. And the result is shown in this dashed line. So after performing this kind of analysis, now we are able to get a more accurate estimation for the form of the spectrum. And it turns out that they're having such kind of oscillatory features have a relatively big impact on the estimation of the action spectrum, as shown in this figure. So this figure again shows that the evolution of the Q as a function of a log. And colored line corresponds to show the the result obtained from the finite difference method. Different colors correspond to the different choices of the range in the fit of the power law. But in any way, if for instance, if we look at the behavior of these green lines, then it fluctuates a lot, and it may lead to some misinterpretation that Q is constant of around 1. But if we use our improved method of the filtering procedure, we instead get this dashed line, which shows the trend that the Q is increasing with log. And so this implies that the one could lead to have some biased conclusion on the behavior of the Q, unless we properly deal with this contamination of the oscillations in the spectrum. And in our opinion, this can be the source of the discrepancy in the literature. Okay. And the third thing we would like to show is the effect of the discretization errors. So this plot shows our final result on the radiation spectrum obtained by the largest simulations. And by performing the simulation with 11,000 cubed, we have now calculated the spectrum at the log is roughly equal to 9, which is shown by this purple line. But if we look at the shape of this spectrum, it looks somewhat strange that the amplitude, there is some reduction in the amplitude in this intermediate momentum. And also we see this strange peak at a very high momentum. And we interpreted them as some unphysical features because of the lack of the resolution of the string core. So the resolution of the string core is parameterized by this quantity MRA, where A is a lattice spacing. But since the lattice spacing grows with time, proportionally to the scale factor, and so the resolution of the string core becomes worse and worse at the late time of the simulations. And according to this resolution issue, spectrum is highly distorted, and the effect is that the spectrum is more power at the IR, and so that the value of the Q can be overestimated because of these discretization effects. And this figure shows the plot of the spectral index as a function of the log obtained by larger scale simulations. And,
5 minutes.
Okay. And we observe that there's a growing trend, but this growth is somewhat pronounced at a larger value of log. And this trend is even more pronounced if we use the smaller simulations with the lower resolution of the string core. So since we cannot use this for the extrapolation, we tried to model this feature by introducing some function which consists of the two functions. One is the true, one is a model for the true evolution of the Q, and the other, but in addition to this, we introduce some function which depends on both log and MRA parameter, which represents a discretization error. And we performed the global fit of the data for some simpler assumptions on the model part. Then we found that basically several different models can lead to a good fit to the simulation result. For instance, we can interpret this trend as a linear growth, which is given by this dashed line. But we can also use a function that behaves like a plateau, 1 over log squared, and approaches some constant at a larger value of the log. And at this moment, it is not possible to judge whether which model is correct. And accordingly, this difference leads to a huge uncertainty when extrapolated to the larger value of log. So I skip the detail of this slide and just give some final result on the extrapolation. So this left panel shows the estimation of the action number divided by the typical estimation of the misalignment contribution as a function of log. And we see that different assumption leads to different results on the action dark matter abundance. And accordingly, there is some difference in the prediction of the action dark matter mass. And since these two trends leads to the almost equally good fit, we assume that these two are two extreme cases for the extrapolation. And we assign the error bars in the action dark matter mass by the difference between these two predictions, which is something like 150 microelectron volt to 500 microelectron volt. And this is basically the conclusion of our study. So, from our opinion, this is a current most sensible estimation of the action dark matter mass ranges. And obviously, in order to be precise, it is very important to have more accurate measurement of the spectral index. But we hope this can be done in the next generation simulations. So let me summarize my talk. So we have performed a dedicated analysis of the spectrum actions radiated from strings. And we have found several systematic errors that could bias the result, which includes initial conditions, oscillations in the action spectrum, and discretization effects. And we are pretty sure that there is a trend that Q increases with log, but its behavior at a large log remains uncertain due to the discretization effects. So maybe further improvement in the dynamical range will be helpful. Okay, let me stop my talk. So thank you for your attention.
Thank you for the nice talk. So anyone has a question? You can raise your hand. So we have a question from Malte. Please.
Hi, Kenichi. Very nice talk. Just a quick question about your MR times A parameter. Do I read it right that if it's equals to 1, your string core width is resolved by one grid side?
Yes, this means that the string core is resolved by one grid size.
Okay, cool.
MRA, A is the lattice space.
Well, this is not exactly, sorry, this is not exactly like this, because the core, so it depends how you define the core.
Okay, okay, yeah. So,
right, so
yeah.
If you say your core is is range in field space where the Higgs field goes from the minimum to half the maximum of the Mexican hat, something like this, then I think for MSA equals to 1, you have almost 4 points in a core. So the diameter is almost 4 points, say 3 point something or something like this.
No, okay.
Yeah.
Do you know what the value was for the simulations that you showed in figure on slide 9?
Sorry, could you say that?
Your figure on slide 9.
Slide 9, okay.
Yeah, do you know what the value for MR times A is in this case? Because you can clearly see like an uptick in the spectrum here as well. I was just wondering if that's related to the discretization effects as well.
Yeah. So in this simulation, around the end of this simulation, MRA is equal to 1. So there can be some discretization effects.
All right, cool.
Yeah, but also there are some effects of the oscillations. So in this case, because we are using a smaller box sizes, so the effects of the oscillations can be even enhanced for the smaller simulations.
Yeah, that makes sense. Cool. Thank you.
Thank you.
Okay, so there another question? So then let's move on to the next. Thank you. Okay. So let's move on to the next talk, which will be given by Kai Murai.
I think David has a question.
Ah, sorry. So David, yes.
Yeah, just wanted to ask quickly, this really great, very interesting work. What's the, okay, so you've now done all these like amazing new simulations at very high resolution, and you said we've got to wait for the next advancement. If I understand rightly, you've been working on fixed grid. What is the next step? Will we ever know if Q is greater than 1 at log of 10 or so? What do you think the next the next step is beyond your work?
Yeah, well, I agree that the using the static lattice is almost saturating because we are using the biggest, basically using a biggest computing infrastructures. So one possible way is, of course, use something like adaptive mesh refinements. So this is one promising direction to go. So by using the other AMR, then even smaller simulation box sizes, we can effectively increase the dynamical ranges. And we hope that in such kind of simulations can have more accurate estimates of the action spectrum.
David, we have actually run one simulation out of log of 10 with AMR, and we're actively analyzing at the moment. So I can't tell you what the result's going to be because we don't actually know, but we have run such a simulation already.
I will wait with bated breath then.